Integrated circuits. In this presentation, we're going to be looking at an introduction to integrated circuits, the different families that exist, unused inputs, applications, and we're going to end with a brief discussion of operational amplifiers. In their most basic and oldest form, logic gates were constructed with standard transistors and resistors. And really we can see that represented here, and that logic gate symbol represents those transistors we see in series with the 3 resistors and the source connections. The disadvantages of a standard assembled logic gate was that there were many wired connections. They're fairly large in size, high cost, low speed, and fairly high power consumption in contrast to what we're going to look at next. New modern logic gates are constructed with microscopic transistors and resistors. And so we can see here the logic gate is inside something called an integrated circuit chip. And that integrated circuit chip will usually have more than one logic gate on it, as well as some other connections. It really depends on the integrated circuit chip we're working with. Let's take a real close view of an integrated circuit chip and see what exactly is in there. So we're going to get closer and closer, and then it's going to transition to a different type of microscope. This is an IC, or an integrated circuit chip, that has had the surface shaved off and polished so that we can then see what's inside the actual unit. It's getting a little blurry here, so it's actually going to transition to a different microscope, an electron microscope, and we're getting closer and closer and closer. And as we get closer, what you're going to notice is that they start to look a little bit electrical in nature. So it looks almost like a city block. There's 1 micron, I think it said, is the distance. These are all teeny tiny transistors, or we could say JFETs or MOSFETs or IGBTs, but they are teeny tiny microscopic connections. So, simply put, an integrated circuit chip is an incredible compressed concentration of standard types of logic gate applications. So, as technology advanced, it became possible to manufacture components much smaller. If these components were only ever used for logic operations, it meant they didn't need to carry large voltage or current values, and this permitted an overall reduction of material used and the size of the equipment. The standard form of this new equipment was a silicon-based integrated circuit, known in the modern era as a computer chip. Now, integrated circuit chips are very reliable, teeny tiny in size, low in cost, high in speed, and very low power consumption. So there is another example of it there. You can see there are connections to items that would connect to a circuit board through solder. And there are 2 different families of integrated circuit chips. They're known as CMOS and TTL. And, well, the difference between these 2 families is how they operate, as in how they're triggered and manufactured, but they also have different threshold values of voltages for both inputs and outputs. In the real world, it's good to understand that a signal is never a perfect 5-volt high or a perfect 0-volt low. Now, each integrated circuit chip has its own specific pinout, which determines where the source, input signals, and output signals should terminate. Pins are soldered to a circuit board or connected into a holder receiver. You can see here a number of different examples. Now, sometimes an IC may come with more inputs than what is required for the intended application of the logic gate. For instance, on this IC, we might have a 3-terminal OR gate, but I only need to use 2 for my application. Well, there's problems that arise if you simply don't use one of the inputs, which wouldn't occur if you just used standard big old chunky logic gates. So an unused input is called a floating input, and this causes problems with the operation of the IC. Depending on the logic gate encountered, unused inputs will be tied high, tied low, or tied together with another input. For OR and NOR gates, unused inputs are tied to another input or to the negative side of the source. This is often referred to as pulling down. And so we can see in this where we've got an OR gate, I got 3 of them, and each of them has a connection back to a device. And if I remove that device, look what happens. The animation is showing red, which means not functioning properly. So it's important that this is tied low. And if it's tied low, then that ensures that the remaining 2 inputs for that OR gate on the integrated circuit chip operate appropriately. For AND and NAND gates, unused inputs are tied to another input or to the positive side of the source, and this is known often as pulling up. So again, here's an example where I have an AND gate. All 3 of them will have to be on or up, or we could say high, in order for the output to go high. And if I remove one of these, we'll notice that the animation will show me that there's a problem and that it's not actually going to function appropriately. So now I'm going to try to operate it, and it says, whoop, problem here, something's not going to function. So what I have to do is I have to tie this to a high source or just tie it to one of the inputs. So this situation, I tied it to one of the inputs instead. You could, however, tie it to the high point on the source, and that would be equally fine for this application. So just another way to deal with an integrated circuit chip if you have an unused input. Now, integrated circuit chips are manufactured for pretty much anything you can think of. Logic gates now come in integrated circuit chips, flip-flops, latches, multivibrators, timers, counters, registers for memory, and operational amplifiers. And remember, registers are used to store bits of data. So today's modern registers come in the form of integrated circuit chips. Instead of having to wire up a whole bunch of flip-flops to make a serial in, serial out, or parallel in, parallel out, you simply purchase the correct integrated circuit. Now, operational amplifiers are used to increase a signal's magnitude and sometimes also to invert it. And so what you can see here is an integrated circuit chip that has the symbol that's used to represent an operational amplifier, which is a triangle facing to the right with a negative and a positive input and a few other connections. You can see here there is an output, there is a positive supply, there is a negative supply, and then there are 2 input terminals. Now there are 2 different categories of operational amplifiers. One of them is known as an open amplifier, and the other is known as a closed amplifier, or closed loop. So we have open loop and closed loop. The way that we can differentiate between the 2 of them is due to the connection of one of the inputs to the output that you see here outlined in red. Now the closed loop operational amplifier will also have a positive and a negative source connection. It just isn't shown as it is on this one. Let's take a look at open loop op amps. Now there are 2 different types of open loop op amps. They're known as the differential and the comparator, and they operate in very similar ways. In this one, the differential, when there is a difference between the 2 input voltages, the output will go into something called saturation, which is equivalent to the power supply voltage. So what we're saying here is that both of the inputs have to be the same value. If one of them is different, then the output goes directly up to whatever the source voltage is for the operational amplifier. It is not going to be a voltage that is in any way correlating to V1 or V2. So in practice, let's say, and I know this is a bit extreme, that I have a 10-volt source for the op amp, and I have an input A and input B of 5 volts and 5 volts. In this situation, because they are equivalent, the output would be 0. Now, as soon as one of these changes, so either high or low, the output goes to saturation, maximum value, which is equivalent to the source that is applied to this operational amplifier. And it doesn't matter if we're going lower or higher, or if there's a big difference or a little difference, the output goes to saturation. An open loop comparator operates almost identical. It's really the same as a differential. However, when one voltage is set as the reference, the other is connected to monitor a voltage. When both voltages are identical, the output is 0 volts. When input voltage is different than the reference voltage, the output will again go to saturation. So here we have a reference voltage of 7 and an input signal of 7 volts and a 10 volt source to the op amp. My output is 0, but as soon as the input goes either above or below, my output goes straight up to saturation. And I apologize, this is an extreme value to be using with my op amp, but it's just a nice, easy number to use for the example. On the closed loop, we have a couple of different types as well. Now, a closed loop amplifier output voltage is not simply 0 or source voltage, as in it's not going to go to saturation. Instead, the output voltage is determined by the size and location of resistors on the amplifier. And so you can see a resistor here, resistor 1, and resistor 2. These amplifiers are used to increase, decrease, invert, or add multiple signals together. So the different types of closed loop op amps are voltage follower, inverting, non-inverting, and summing. And I should caution, I'm not going to go through the calculations in this presentation because for the average electrician, simply a general awareness of the types is sufficient. The calculation is typically not something that we're going to really need to know. So here's the closed loop follower. You'll notice that the output is identical to the input signal. There are no resistors in here. It's simply boosting the signal slightly sometimes, but it is just isolating the left from the right. On this one, I've got a closed loop inverting amplifier. You'll notice there are resistors connected in here, and you'll notice that I am connected to the inverting input terminal, the negative terminal. If I connect into the negative terminal, it means that the signal will be inverted. Notice I start with a positive alternation. Over here, I start with a negative alternation. I have resistors, which means that dependent on the size of those two resistors, I could have control over how much this signal is amplified. Here's a closed loop non-inverting amplifier. The only difference you can see is that my input signal is on the positive non-inverting terminal. And so I start with a positive alternation, and I have a positive alternation here. So again, this one has resistors, which means that dependent on the size of them, I could control how much bigger this output signal is from the input. And finally, a closed loop inverting summing amplifier. In this situation, I am taking 3 separate signals coming in with 3 different resistance values into the inverting terminal, and the output will then be the sum of those 3 signals. Now, how much of each signal is added is going to be dependent on the size of each of these resistors. If each of the resistors is equivalent in size, then an equal value of signal will be added together. If there are differences, then that will vary the percentage or quantity or amplitude that I'm adding from each of these 3 signals, which will then result in the output over here on the right-hand side of the op amp. So, this has been integrated circuits and some of the applications that we use them in the electrical field.